Welcome back to the Deep Dive. This is where we take those dense, often overwhelming technical landscapes, stack up all these essential facts and research, and, give you the shortest path to being truly well-informed.
And today, we are strapping in for a big one.
We really are. We're doing a focused expedition into Google Kubernetes Engine, or GKE as everyone calls it.
Kubernetes can feel like the deep unknown. It's like this massive, sprawling container city. It's incredibly powerful, but that complexity, I think, makes people hesitant. They worry about getting lost in the weeds of, YAML files and all the component configuration.
Absolutely. And that's exactly why our mission today is so laser-focused. We are cutting through all that noise. We are not talking about generic Kubernetes today.
Yeah.
We are concentrating purely on the Google Cloud implementation, GKE. So if you're prepping for that critical meeting, or maybe you're just starting your journey into container orchestration, and you really need to understand the critical why behind GKE's most powerful features, well, this is your foundational map.
That's the goal. We've distilled all the material covering, everything from the fundamental deployment choices all the way up to advanced scaling metrics and crucial security controls.
So the idea is to clarify the essential terminology, right?
Right, and provide those clear analogies you need for that aha moment. We want to give you the foundation necessary to confidently tackle both basic and even intermediate GKE questions.
That sounds like a solid shortcut. So let's unpack this. Let's start right at the very beginning. The first foundational choice you have to make when you commit to GKE. Which operational mode should you choose?
Okay, but before we even get into the modes, let's just quickly re-anchor the GKE value proposition.
Good idea.
So Kubernetes provides these open standards for container orchestration. You package your application into a container once, and Kubernetes manages its deployment, networking, and scaling, theoretically, anywhere. GKE is simply Google Cloud's official, highly optimized, and integrated implementation of that standard.
And the level of managed is really where that fundamental decision point lies. This brings us to that fork in the road you mentioned. GKE standard versus GKE autopilot.
It really is a fork in the road.
I love thinking about this in terms of real estate, actually.
That's a great way to put it. It's an essential distinction, so let's use that framework.
Okay, so think of GKE standard as owning a technical condominium. The Kubernetes control plane is kind of like the condo association. They manage the shared structure, the central services, the central brain of the cluster.
Right.
But you, the owner, are responsible for the infrastructure within your unit.
And in GKE terms, standard implies that you are the one responsible for provisioning and managing the underlying compute engine instances, those virtual machines that we call nodes. This is where all that operational burden really sits.
Okay, so what exactly does that operational burden entail for someone using standard mode? What am I actually doing day to day?
Oh, it's significant. You are responsible for the health of those VMs, so that means patching the OS, managing the cluster version upgrade schedule, and I think most importantly, capacity management.
Capacity management.
Yeah. You have to ensure you are efficiently fitting as many containers, which we call pods, onto the smallest number of VMs possible to save money. This whole process is known in the industry as bin packing.
And that sounds like a constant headache.
It is. It's a constant headache of optimization. You get total granular control over machine types and sizing, which is powerful, but you absorb all the operational responsibility for that entire infrastructure layer.
So standard is really for the customer who needs that fine-grained control over the machine type. Maybe they need specific GPU models, or they have specialized network interfaces, and crucially, they have a dedicated team to manage that capacity and maintenance.
Exactly. Now, compare that to Autopilot. Autopilot is the fully managed hotel suite. You get all the luxurious amenities, the power and portability of Kubernetes, but you do not have to lift a finger for the infrastructure.
That sounds very compelling. So what does Autopilot take off my plate specifically?
Well, basically everything related to the nodes. You don't worry about OS patching. You don't worry about capacity planning or bin packing efficiency, or even creating the nodes in the first place.
So when my app needs more resources?
When your application needs more resources, GKE just automatically provisions the appropriate node resources in the background. Google takes care of the floor, the walls, the utilities, the cleaning, all of it entirely. The why for Autopilot is just pure operational simplicity.
Okay, if operational simplicity is the goal, let's talk money. How does the billing model reinforce that difference?
It's completely different. In GKE standard, you are billed for the underlying VMs, period. It doesn't matter whether those machines are 10% full or 90% full, you pay the flat rate for the VM time. If you mismanage your bin packing, you are just wasting money.
And Autopilot?
Autopilot changes this entirely. It features a pay-for-what-you-request model, so the billing is handled at the pod level. You pay only for the CPU and memory resources that your container actually requests, not for the entire machine it happens to be running on.
That sounds like a dream for cost optimization, but, I have to ask about the trade-offs, because nothing is ever perfectly easy. If I choose autopilot, am I sacrificing something crucial?
You are. You're trading control for convenience. You get less control over the underlying machine type and less flexibility in configuring low-level node settings, which might affect, highly specialized networking or proprietary hardware needs.
And what about on the cost side?
Well, on the cost side, while it's consumption-based, if your developers are lazy and they request far more resources than their application actually needs, you can end up overpaying for underutilized requested capacity. So you have to be disciplined about your resource requests.
That is vital context. Now, here's a scenario that I think confuses a lot of people entering this space. If autopilot is so easy, why not just use Google Cloud Run? I mean, Cloud Run is also incredibly easy and serverless. When does the need for GKE, even autopilot, become critical?
This is a classic intermediate level decision point, and it's often triggered by a migration from a serverless platform to GKE. The core reason is always that control trumps convenience for performance-critical applications.
Okay, so what specific application requirements would force that kind of migration?
There are three main factors. First, and this is often the biggest one, cold start latency. While serverless is great, if an instance has to spin up from zero to handle a request, you get latency. A little delay.
And for some apps, that delay is a deal breaker.
Exactly. If that brief delay is absolutely unacceptable, maybe for a premium B2B API or a real-time gaming backend GKE, provides a solution where pods can be kept perpetually active and instantly responsive.
Now, I know Cloud Run can mitigate this with min instances to keep things warm, so what's the thing that pushes GKE over the edge?
It's the combination of that instant availability plus two other control requirements. The second one is you might need granular control over specific networking protocols.
Like what?
Like gRPC for really efficient internal communication or persistent connections using WebSockets. GKE provides the deepest native control over these protocols, allowing you to really fine-tune the connection handling.
Okay, so latency and specific network protocols. What's the third requirement?
Consistent resource availability. For premium applications, you need guaranteed, consistent CPU availability that goes beyond the sort of burstable model sometimes offered by pure serverless. GKE, through its explicit resource request structure, guarantees that availability.
So GKE becomes the necessary destination when performance, specific protocol management, and guaranteed CPU consistency are paramount, even if it reintroduces a slight layer to complexity compared to basic serverless functions.
That's it in a nutshell.
All right, so since we've decided on GKE, maybe even autopilot, because we need that deep control or we just want Google to handle the nodes, well, that frees us up to concentrate purely on the application's lifecycle.
Exactly.
So let's start with how we actually build and deploy that base layer. We have these two critical tools that always come up, Juget Cloud and Kubectl.
And this is a point of frequent confusion for newcomers. You really need to understand that Kubernetes infrastructure management and application management live in two separate worlds, and they require two separate tool sets.
Okay, so let's start with the infrastructure then. Action 1.
Action 1 is cluster creation, and this is done using the Google Cloud command line utility, jugcloud. This is the tool that speaks to the Google Cloud Platform API. It's what provisions the underlying VMs, sets up the VPC networking, and deploys and manages the entire Kubernetes control plane. It's the infrastructure architect.
So jugcloud is what lays out the physical grid and constructs the shared infrastructure. It literally creates the city. And once the city exists, we move to Action 2, placing our application inside of it.
And that's when you switch tools. You use the native Kubernetes command line interface, Kubectl. This tool speaks directly to the Kubernetes API server inside the cluster you just created.
And what resource does Kubectl typically create to actually house the application?
The primary resource is the deployment. The deployment resource defines the desired state of your application, which container image to run, how many replicas should be running, and all the critical details about resource requests and limits.
So the essential workflow is use QCloud to build the cluster, then use Kubectl to apply the deployment resource into that cluster. That separation of concerns, cloud management versus Kubernetes internal orchestration, that seems like a key concept to internalize.
It's absolutely fundamental. Now let's tackle the immediate operational challenge that comes right after deployment: zero downtime updates.
Right. Our developers have a new image. How do we swap the old version for the new one without users experiencing an outage?
Well, we can't just delete the old pods and launch the new ones.
No, that would create a gap in service availability, a big one.
Exactly. The recommended and frankly simplest method is leveraging Kubernetes built-in smarts via the command kubectl set image deployment name new image. This command initiates what's called a rolling update.
Okay, so what exactly happens during a rolling update? How does Kubernetes ensure that gentle swap?
Kubernetes manages the transition very gracefully. It adheres to parameters that are defined in the deployment, often implicitly, things like max unavailable and max surge.
What do those mean?
Well, max unavailable is how many old pods can be offline at any time, and max surge is how many new pods can be created above the desired replica count. So Kubernetes introduces a new pod, it waits for it to be confirmed healthy, and only then does it terminate an old pod. This continuous overlap ensures service availability remains high.
But a rolling update is only safe if that new pod is truly ready before traffic hits it. What if the new container image has a bug or, I don't know, it takes too long to initialize? That's where the prevention mechanisms come in, right?
That's right. This is where we must talk in depth about liveness and readiness probes. These are configuration settings within the pod specification that determine the container's health and its eligibility to receive traffic.
Let's define the liveness probe first. What question is it asking?
The liveness probe is asking a very simple question. Is my application fundamentally operational? Is the process still running or is it deadlocked? If that probe fails, say the application just freezes up, Kubernetes sees this as a failure, assumes the container needs resuscitation, and it initiates a restart.
So it's the watchdog.
It's the watchdog ensuring the container remains fundamentally alive.
Okay, so the liveness probe ensures continued operation. Now, the readiness probe, how does this differ and why is it so essential for zero downtime rolling updates?
The readiness probe asks a different, more subtle question. Is my container ready to accept user traffic? And this distinction is critical. A container can be alive, the liveness check passed, but not yet ready to serve requests.
Like it's still booting up.
Exactly. Perhaps it's downloading data, or initializing a large cache, or waiting for a downstream database connection. If the readiness probe fails, Kubernetes keeps that pod out of the service load balancer rotation.
I see. So during a rolling update, Kubernetes launches the new pod. The liveness check passes. It's breathing, so to speak, but the readiness check fails for, say, 30 seconds while it boots up. Kubernetes just holds off directing traffic to that pod until the readiness check finally succeeds.
Exactly. This is what prevents users from hitting an application instance that is still initializing or is misconfigured. In fact, misconfigurations during rollouts almost always stem from the readiness state being ignored or, just set incorrectly.
What are some common pitfalls here? For instance, I've heard that sometimes people can make their liveness checks too aggressive, maybe checking every single second.
That's a perfect example of a common operational pitfall. If your liveness check is too aggressive, or if the check itself is too resource intensive, you can create a situation called resource thrashing.
Resource thrashing.
Yeah, the container spends all its time processing the health check, or a temporary spike in load causes the liveness check to fail, leading Kubernetes to needlessly restart the pod over and over and over. It ends up causing availability issues, not solving them. The checks have to be lightweight and configured with appropriate initial delays and failure thresholds.
We have successfully deployed our app using liveness and readiness probes to ensure a safe rollout. The next major challenge in any cloud environment is, of course, scaling efficiently to handle fluctuating load.
Right.
And we have to scale two layers here, the application itself and the underlying infrastructure.
That's a great way to put it. It's the difference between hiring more staff and expanding the office building. If you only hire more staff but the building is full, the new staff is useless.
And if you only expand the building but don't hire staff, you're just paying for empty space.
Exactly. And Kubernetes provides coordinated autoscalers for both of those layers.
Okay, let's start with layer one, scaling the application or the pods.
That is the job of the Horizontal Pod Autoscaler, or HPA. Its mandate is very straightforward. Automatically adjust the number of pod replicas, your application instances, based on observed demand.
And what's the typical trigger for that?
The default and most common trigger is target CPU usage. You might configure it to, say, 50% utilization. If the average CPU load across all the running pods consistently hits that 50% mark, HPA increases the replica count to distribute the load and bring that average utilization back down.
So HPA is watching the workload of the staff. If they look too busy, HPA automatically hires more staff. But as you mentioned, if HPA tries to hire more staff, but the existing office buildings and the nodes are full, what happens then?
Well, that's the treatment for layer 2, scaling the infrastructure, or the nodes. This is handled by the Cluster Autoscaler. The Cluster Autoscaler is constantly monitoring for unschedulable pods, those new pods created by HPA that just don't fit on the existing nodes.
So when it sees that bottleneck,
When it detects that resource bottleneck, it automatically adds or removes the underlying compute engine instances, the VMs in the cluster's node pool.
so the critical synergy here is that HPA generates the demand for resources, and the Cluster Autoscaler is the supply mechanism that reacts to that demand.
Yes. They must be enabled together to achieve automatic elasticity based on CPU.
That makes perfect sense.
And while HPA is configured via a normal Kubernetes API object, the Cluster Autoscaler has to be explicitly enabled on the cluster infrastructure itself. This often uses the dcloud command, something like gcloud alpha container clusters, update cluster name, enable autoscaling min nodes and max nodes M.
And you have to define that acceptable range.
You do. You have to set those safety guardrails for the number of nodes the cluster can scale between.
So that min nodes and max nodes setting is essentially your budget and performance guardrail, isn't it? You're telling GKE, never go below this number to maintain resilience, and never go above this limit to protect my wallet.
That's exactly right. It's the balance between cost control and availability guarantees.
Okay, now let's move into advanced scaling, because this is fascinating. We've talked about CPU scaling, which works great for stateless web APIs. But what if the workload is I/O-intensive batch processing? Let's say crunching messages pulled from PubSub and storing the results in file store.
Right.
In that case, CPU usage might sit pretty low, but if the incoming message queue explodes, we're still bottlenecked.
This is the perfect use case for scaling based on business metrics. Standard CPU scaling is just insufficient because the real workload is defined by the volume of messages waiting, not just how hard the CPU is working at any given moment.
So if the line of work waiting is the true metric of load, how do we connect that waiting line, the PubSub backlog, to the Kubernetes HPA?
We configure HPA to scale based on a custom metric, specifically the subscription annulled messages metric, which is provided by PubSub and exposed through cloud monitoring.
Okay, help me understand the mechanism here, because this is where the different tools connect. How does HPA, which lives inside the Kubernetes cluster, know what the PubSub backlog is when that backlog lives outside the cluster?
Well, GKE integrates very deeply with Google's observability suite. The key is the cloud monitoring API, which aggregates all these custom metrics, including the PubSub backlog. HPA can be configured to just query that API.
And if the backlog grows past a certain threshold?
Yep. Let's say it grows past 10,000 undelivered messages. HPA sees this and automatically triggers the scale-up of the processing deployment.
That is an elegant solution. It means we are scaling purely based on the actual business workload, not just a generic technical metric.
And when the backlog drops, the system scales back down, saving money while ensuring low queue processing latency. It's the definition of efficiency for message-driven applications. You are making your infrastructure directly responsive to the source of the demand.
Okay, so scaling is in place, which means our application can handle large user loads. The next deep topic is networking. How does traffic flow internally, and how do we safely expose our services externally? This area often feels like a complete black box to people who are new to GKE.
It's complex because we're trying to provide stability in an environment that is defined by constant change. Let's start with internal microservice communication.
Okay, so we have Service A and Service B running inside the cluster. Service B's pods are constantly changing their IP addresses because of scaling and restarts. So how does Service A reliably find and talk to Service B?
The answer is Kubernetes abstraction using the service resource. You deploy Service B as a deployment, that's the running pods, but you expose it using a service resource, typically of the cluster IP type, which means it's internal only.
And what crucial piece of information does that service provide?
It provides a stable cluster internal IP address and, more importantly, a service DNS name.
A DNS name.
Yes. Service A doesn't try to track Service B's individual pod IPs. It just addresses it using a consistent DNS name, for example, inventory-service.default.svc.cluster.local. This DNS name resolves dynamically to the cluster IP, which then load balances requests across all the available pods for Service B.
So that's the abstraction layer. The service is the constant address book entry for the ever-changing pods. Okay, let's move external. How does the outside world, our internet users, reach the application running inside our cluster?
Well, we have a couple of primary options, and they're determined by the type of traffic. The modern standard approach for web traffic is ingress.
Option 1, ingress.
Right. Ingress is a Kubernetes resource that manages external access to services in a cluster, typically HTTP and HTTPS traffic. In GKE, Ingress often provisions a managed HTTPS load balancer on Google Cloud, handling things like SSL termination and intelligent routing to the correct service. It acts as the intelligent L7 or application layer entry point.
But there must be scenarios where ingress isn't sufficient. We need to fall back to a more targeted service type. So, option 2, service of type load balancer. When would this be required?
This is a requirement almost always driven by legacy systems. The specific use case we see frequently is migrating an older internal application that relies on a hard-coded static internal IP address for a backend service.
Ah, so maybe a decades-old system that expects a server to always be at 10.10.5 by 20 or something.
Exactly that. So we need GKE to provision a load balancer. But that load balancer needs a guaranteed, non-changing internal IP address. To achieve that specificity, we use the load balancer service type in the Kubernetes definition.
And how do we tell it which IP to use?
Critically, we add a specific static IP annotation. GKE recognizes this annotation, and it provisions a dedicated internal load balancer that secures that required static internal IP address within your VPC, satisfying that rigid legacy constraint. It's GKE's way of accommodating infrastructure debt.
That's a highly specific, but I'm sure very common migration bridge. Let's take the complexity up another notch. Global reach.
Right.
We have a highly successful stateless web API in the US region, let's say Central 1. We just launched in Asia, and users there are reporting unacceptable latency.
Well, low latency for a global application means serving traffic from proximity. You have to replicate the application closer to the users.
Okay, so we create a second GKE cluster in, say, Asia Southeast 1. But users still need to access us via a single domain name, and we need to ensure they are routed to the nearest lowest latency cluster automatically.
This requires kubemchi, or Kubernetes multi-cluster ingress. This tool extends the concept of ingress across different geographically separate GKE clusters. When you configure kubemfi, it provisions a single unified global HTTPS load balancer on Google Cloud that spans both your US Central 1 and your Asia Southeast 1 clusters.
And that global load balancer is intelligent enough to perform geo-routing. It knows where the user is coming from.
Absolutely. It directs the user to the closest healthy instance, which ensures minimal latency and also provides critical redundancy should one region experience an outage. It creates a seamless global application platform out of separate regional clusters.
Okay, finally, let's hit a critical security constraint. The private cluster requirement. Our security mandate is absolute. No GKE nodes, no compute engine instances are allowed to have a public IP address. But our application still needs to reach third-party internet services, like update APIs or payment gateways. How does a private node talk to the public internet?
This constraint immediately forces you to configure the GKE cluster as a private cluster. Since the nodes reside exclusively within your virtual private cloud, your VPC, with only internal IPs, they can't initiate traffic to the public internet directly.
So we need a managed secure exit strategy for any outbound traffic.
Correct. The solution is to configure a dedicated Cloud NAT gateway, that's network address translation, for the cluster subnet. The private nodes route all their desired outbound traffic to this Cloud NAT gateway.
And the NAT handles the public part.
Exactly. The NAT then translates the internal node IP address to a secure public NAT IP address, allowing the traffic to exit and return safely, all without ever exposing the individual nodes to the public internet.
So CloudNet acts as the controlled, secure choke point, preserving security compliance while ensuring necessary external connectivity. That's a great deep dive into the intertwined worlds of security and networking.
It really is.
We've focused heavily on scaling and networking stateless workloads, but containers often need to manage state. That means they need consistent identities and persistent storage. How do we handle these stateful workloads in GKE?
Well, the standard Kubernetes resource for this is the stateful set. A standard deployment treats every pod as fungible, identical and disposable. If pod A dies, the replacement is just another generic pod B. A stateful set is fundamentally different because it's built for coordination.
Okay, how does a stateful set maintain that coordinated identity?
It ensures that each pod instance receives a unique, stable network identity, so consistent host names, and it guarantees ordinality, a specific number like 0, 1, 2. If the pod DB1 crashes and restarts, the replacement pod will still be named DB1.
And why is that so important?
Well, this stable identity is non-negotiable for distributed data stores like Cassandra or Zookeeper, which rely on quorum and fixed identities to elect leaders and maintain a consistent state.
And stateful sets are often paired with a separate storage resource, right? They don't store the data themselves.
Yes. They are almost always paired with persistent volumes, PVs, and persistent volume claims, PVCs. The PDC ensures that the data stored by a stateful set instance remains durable. If pod DB1 is destroyed, the persistent volume persists, and it's ready for the new DB1 pod to connect to it when it relaunches.
That addresses data that lives inside the cluster. Now let's look outside. We have an application in GKE that needs to connect securely to a managed service, specifically Cloud SQL, which is Google's managed relational database. We can't expose the database port publicly. That's a huge security risk.
Yeah.
What's the standard secure connection pattern?
For this, we use the Cloud SQL proxy container, and we leverage the powerful sidecar pattern in Kubernetes.
So the application container and the Cloud SQL proxy container run together in the same pod. Why in the same pod?
Because containers within the same pod share the same network namespace and storage volumes. This allows the application to communicate with the proxy securely over localhost. The proxy handles the complex part, managing secure, authenticated, encrypted connections to the Cloud SQL instance using service account credentials.
So the application container itself never needs to worry about handling SSL certificates or exposing raw database credentials.
Never. It just talks securely to localhost, and the proxy handles all the rest.
That significantly simplifies the security posture. Now, let's assume the application is reporting intermittent database connection errors. We need to perform a rapid postmortem. Where is the single most efficient source of truth for the failure analysis?
When you're troubleshooting complex cross-service issues, especially GKE talking to a managed service like Cloud SQL, you absolutely must rely on the unified logging and monitoring infrastructure. Stack driver logging, which is now consolidated under cloud logging and monitoring.
And specifically, what logs should the SRE be prioritizing? Where do they look first?
You need to correlate data from both services. So first, you check the stack driver logs for the specific GKE container pod. This will reveal if the application container is failing to connect to the proxy, or maybe if the proxy itself is failing to start up or authenticate.
And at the same time,
Simultaneously, you have to check the Cloud SQL logs to see if the connection was actively rejected by the database. Maybe it was due to incorrect permissions or network configuration errors, or perhaps the database was simply overwhelmed and overloaded.
so the correlation of those two log streams is key to pinpointing whether the failure is client-side in GKE or server-side in Cloud SQL.
Absolutely. The unified system is what makes that correlation possible and efficient.
Let's end this section on modernization.
Sure.
We have a classic migration problem. We're moving a legacy Linux VM environment to GKE, but the team lost the original source code years ago. We can't manually create a Docker file to define the environment. How do we containerize this black box?
This is a scenario that is tailor-made for a specialized tool. Migrate to containers, which is now part of Anthos. This tool solves that fundamental problem of missing source code.
So how does it manage to create a container without a Docker file? What's the magic?
It performs an automated discovery process. It inspects the existing Linux VM environment. It analyzes the operating system, the installed binaries, the configurations, the service dependencies, and then it automatically extracts and converts that entire operational state into a runnable Docker container image and the necessary Kubernetes configuration files, like the deployment YAML.
So it's like it takes a snapshot of the essence of the running server and just packages it up.
Pretty much. And that allows us to leap from a rigid monolithic VM to a containerized application in GKE quickly and with minimal risk, even if the source code is long gone.
Once the application is running, the real operational challenge begins. Maintaining consistency, security, and quality through the automated development lifecycle, or CI/CD.
Yes, this is where the rubber really meets the road.
Let's architect a robust CI/CD flow. The goal is automation. When code is pushed to the GitHub develop branch, we want it built, tested, and automatically deployed to the development cluster.
The process starts in Google Cloud by defining the trigger. You create a cloud build trigger that is specifically configured to monitor push events on the GitHub repository's develop branch.
Okay, so Cloud Build takes over from there. What's the sequence of steps?
Cloud Build executes the build steps, running tests, successfully building the container image, and then storing that finalized image in the container registry or artifact registry now.
Okay.
However, we must adhere to a crucial security best practice when deciding the final step.
And that best practice is separating the build from the deployment. Why is that so important?
It's the principle of least privilege and segmentation. We mandate that only a dedicated deployment tool or a specific service account should have the necessary permissions to deploy new versions to the cluster. Cloud Build itself should only have permission to build and store the image.
And why is that separation critical?
Well, think about it. If the build environment were compromised, the attacker would have the ability to push a malicious image to the registry, but they would lack the permission to actually deploy that image to the sensitive development or production clusters. This is a critical security boundary.
That segmentation makes a lot of sense. Now, let's address the ultimate production nightmare, an untested image skipping the entire QA process. Let's say developers are able to deploy untested images directly to the production cluster. How do we implement an ironclad security gate to enforce that development, staging, production, promotion path?
This requires hard, policy-driven governance. And the tool for that is Binary Authorization. It's essentially a checkpoint that enforces code promotion requirements before a container is even allowed to run.
Binary authorization sounds complex. Let's maybe use an analogy to break down the mechanism.
Okay, think of it like this. Your container image is traveling around the world, but it can't enter a new country, a new cluster, without the right passport stamps, and we call those stamps attestations.
Okay, so you configure binary authorization policies on all your clusters.
On all of them. And an attestation is basically a digital signature or a stamp of approval that's generated by a trusted authority, a piece of code proving that a specific step was successfully completed for that container image.
So examples might be unit tests passed or vulnerability scan passed.
Exactly. Or most critically, deployment approved after passing user acceptance testing in the staging environment.
And the CI pipeline's what generates these stamps.
Yes. The CI pipeline, after a successful deployment and validation and staging, generates that digital attestation. The production cluster policy is then configured to only allow images with a specific set of required attestations. Specifically, the one proving the image was vetted in staging.
So if a developer tries to deploy an image that lacks that critical digital stamp, binary authorization just refuses to launch the container.
Instantly. It enforces the compliance requirements automatically. It is a minimal effort, maximum impact security solution. It shifts enforcement from, procedural documents to automated infrastructure policy.
Okay, moving from security to resilience. We need to test what happens when a key microservice fails catastrophically. We need controlled failure testing. We can't just unplug a server, even in a testing environment, because that's disruptive and hard to reproduce.
This is a job for chaos engineering, specifically using a service mesh like Istio. We use Istio's fault injection feature.
How does fault injection differ from just killing a pod? It sounds similar.
Istio doesn't destroy the underlying infrastructure. Instead, it operates at the network level, allowing you to configure virtual faulty behaviors for a specific microservice. You can tell the network 10% of requests to service A should be dropped, or inject 5 seconds of latency into all requests to service B.
So we are testing the downstream service's ability to handle graceful degradation, making sure the application doesn't collapse entirely if one component is slow or unresponsive.
Precisely. It provides controlled, non-disruptive, and highly reproducible testing scenarios, which is essential for hardening complex microservices architectures against real-world failures.
And finally, we have to confirm the system's capacity. We need assurance that our application handles tens of thousands of users and that latency remains below a strict, maybe even a contractual threshold.
Yeah.
What is the definitive, non-negotiable step here?
The definitive measure for capacity assurance is straightforward. You must use a dedicated load testing tool. There is no shortcut, there's no dashboard that tells you this definitively.
And the goal of that tool
is to simulate the expected number of concurrent users and the total volume of requests you anticipate during peak load conditions. You then measure the empirical response times and error rates against your service level objectives, your SLO, to prove that the system works under pressure. Autoscaling is a theory, load testing is the proof.
The application is built, secured, and tested. The final critical stage is continuous operations, monitoring, diagnosis, and perhaps the most sensitive part, cost management.
Let's start with SRE triage. An incident occurs. Time is ticking. Where should the site reliability engineer go first to gain immediate high-level visibility?
I would assume straight to a logs, but I have a feeling there's a better starting point.
There is. The fastest path to triaging an incident is the predefined dashboards in the cloud monitoring workspace. GKE automatically populates these dashboards with critical metrics, CPU utilization, memory usage, network latency, and request error rates across the entire cluster.
So this gives you the high-level context. Is it a CPU issue or a network issue before you had to dive into the specific details in the log?
Exactly. It provides the necessary context for the investigation.
Let's take a specific failure scenario. We have an unresponsive application, and we notice its pods are trapped in the infamous crash loop, restarting every few seconds. The container writes its logs to standard output. Where is the root cause documented?
Well, the crash loop is a container startup failure. Since containers write to standard output, which is collected by the GKE monitoring agent, the root cause is always in the Stackdriver logs cloud logging, specifically filtered by the GKE container pod that is restarting. You need to see the exact error message or the stack trace that caused the process inside the container to exit immediately.
So looking at node logs or system logs is too far removed.
Way too far removed from the actual application process.
Perfect. Now, a scenario involving operational debt. We've been running this cluster for 2 weeks. Customers are reporting intermittent errors, but due to an oversight, we currently have no centralized logging or monitoring enabled on the GKE cluster. We need to diagnose the problem retrospectively with minimal disruption.
Minimal disruption is the key constraint here. We can't just create a new cluster and migrate everything. The fastest, lowest disruption path is to perform an in-place update.
And update the existing cluster to enable what exactly?
You update the existing GKE cluster to enable the full cloud operations for GKE Suite. This is a non-disruptive update that activates the built-in logging and monitoring agents across all the nodes.
And once it's enabled?
Once enabled, you immediately gain access to the dashboard and, crucially, begin collecting fresh logs and metrics, allowing you to quickly investigate the intermittent errors affecting those specific pods.
Okay, that addresses the operational side. Let's finish with the critical subject of cost optimization. We have a massive established cluster, say 200 nodes, and it's running a mix of workloads. How do we reduce the cloud bill without compromising availability or performance?
A single gigantic node pool like that is almost always inefficient because you are paying for unused capacity. The strategy for cost reduction has to center on right-sizing both the application layer and the infrastructure layer via coordinated autoscaling.
So fewer staff when demand is low, and a smaller office building to match that.
Exactly. The strategy has two primary components. First, you must implement the Horizontal Pod Autoscaler across all of your stateless workloads and any compatible stateful processing workers. This ensures that during low-demand periods, you are only paying for the minimal number of running application instances necessary.
And the second action focuses on the infrastructure cost itself.
You have to ensure node autoscaling. The Cluster Autoscaler is fully enabled. When HPA scales down the pods during off-peak hours, the underlying nodes naturally become underutilized. The Cluster Autoscaler detects this, it drains the excess node, and it safely removes the unnecessary underlying compute engine VMs, which directly reduces your cloud bill.
So that HPA and Cluster Autoscaler tandem is the ultimate cost optimization strategy for flexible GKE workloads.
It really is. It's teaching Kubernetes how to manage its own economy-matching supply to demand dynamically.
We've covered extensive ground today. Moving from the philosophical decision of standard versus autopilot, which defines your operational responsibility, all the way to highly specific implementations for security, networking, and data management.
It's a lot.
To quickly synthesize, we now understand the necessary handoff between Kaffilia Cloud for infrastructure and Kubectl for application state, and the absolute necessity of coordinating the Horizontal Pod Autoscaler, which is application demand, with the Cluster Autoscaler, which is infrastructure supply.
And we also clarified why certain tools are non-negotiable, using stateful sets for that guaranteed identity, and the Cloud SQL proxy for secure data access.
And we clarified that the advanced decisions like using binary authorization to enforce policy via attestations or deploying CloudNet for private clusters are always driven by strict application requirements, whether for security, compliance, or extreme performance needs like that gRPC cold start migration scenario.
You now have the foundational map of GKE. You understand why these specialized tools are chosen, and it's based entirely on the specific application requirements they solve.
Which brings us to our final provocative thought for you to chew on.
We learned earlier about achieving global reach using kubemchi, which creates a single global HTTPS load balancer spanning multiple regional clusters, say, one in the US and one in Asia.
Right. And given that we need that global front door, but our security team mandates that our US cluster must be a private GKE cluster, relying on a centralized CloudNet gateway for all its external communication.
How does that strict security requirement, that need for the CloudNet exit strategy, impact the multi-cluster writing architecture provided by Kubemshi? Specifically, does the traffic from the global load balancer coming from the public internet successfully reach the private U.S. cluster's services? And what complex networking configuration is required to thread that needle between maximum security and global performance?
It's a deep question that reveals how networking, security, and global architecture are always challenging interconnected layers in the cloud. Something to ponder as you continue your deep dive into GKE.
Thank you for joining us on the Deep Dive.
We'll see you next time.